Hello there, and a quiet welcome to the Science Owl Station. Tonight, we aren't going to discuss the loud, explosive parts of the universe. Instead, we're going to sink into its deepest, most silent corners. We're going to talk about cosmic pressure and the strange, dense objects it creates. Imagine, for a moment, the ultimate act of stellar housekeeping. A star so massive, after a life of brilliant fusion, finally gives in. Its core collapses, not into nothing, but into something so impossibly compact, it defies everyday logic. All that remains is a city-sized sphere containing more mass than our sun. This is the birth of a neutron star, and surrounding this entire process, an invisible, relentless sculptor is at work. Pressure. Not the kind you feel before a deadline, but the fundamental force that holds galaxies together, that crushes atoms into new forms, that writes the life and death of every star in the cosmos. This journey through 100 sleepy facts is an exploration of these two concepts: the ultimate compact object and the ultimate cosmic force. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you'd like, leave a comment telling me where you are in the world right now and what time it is there. I always find it wonderfully grounding to picture listeners drifting off from different corners of the globe. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. Our first fact, the one that sets the stage for this entire dreamlike catalog, is about origins. A neutron star isn't a star in the way we think of our sun, a blazing ball of ongoing fusion. It is a stellar remnant, a cosmic ghost. It's what's left after a giant star, one at least 8 times more massive than our own sun, exhausts its nuclear fuel. The outward pressure from fusion vanishes in an instant. For millennia, this pressure had fought a graceful tie against the star's own immense gravity. Now gravity wins, catastrophically. The core implodes at nearly a quarter the speed of light. The outer layers rebound in a supernova explosion visible across galaxies. But the core, it doesn't vanish. It's squeezed and squeezed and squeezed some more until protons and electrons are forced together, merging into neutrons and neutrinos. What remains is a ball of nearly pure neutrons, a few dozen kilometers across. It's a zombie star, dead in terms of fusion, but pulsating with a fierce residual energy. This leads us naturally to our second fact, which attempts to quantify this unimaginable density. If you could somehow scoop a single teaspoon of material from the heart of a neutron star, just a regular teaspoon from your kitchen drawer, and bring it to Earth, it would not weigh a few grams. It would not weigh a few kilograms. That one little teaspoon would have a mass of about 1 billion tons. To put it in a more poetic, sleepy scale, it would weigh more than Mount Everest. Every single grain in that hypothetical teaspoon would be a neutron, packed shoulder to shoulder with its neighbors, with no empty space. No atoms as we know them, just a continuous, swirling ocean of subatomic particles. The third fact is about the surface of this impossible sphere. Given the chaotic violence of its birth, you might imagine it as a cracked, mountainous, turbulent landscape. But the physics of such immense gravity dictate otherwise. The gravitational pull on the surface of a neutron star is about 100 billion times stronger than Earth's. This force is so unimaginably potent that it smooths out imperfections with brutal efficiency. Any mountain range, any significant deviation from a perfect sphere would be instantly flattened. Astronomers estimate that the tallest possible mountains on a neutron star are mere centimeters high, tiny, imperceptible wrinkles on an otherwise almost flawlessly smooth ball. It is quite possibly the smoothest solid object in the entire galaxy. Now, this dense, smooth sphere isn't just sitting still. Fact number 4 introduces its furious spin. Like a figure skater pulling in their arms to spin faster, the collapsing core of the progenitor star spins up dramatically as it shrinks. A star that might have rotated once every few weeks can become a neutron star spinning hundreds of times per second at its birth. Imagine that an object with the mass of a sun, wider than a city, completing a full rotation in the blink of an eye. This rapid spin is a key part of its identity and leads to some of its most famous manifestations. Finally, for this opening set, Fact 5. The magnetic personality. During the collapse, the star's original magnetic field gets concentrated and amplified, wound up tighter and tighter. The result is a magnetic field of mind-numbing strength. A typical neutron star's magnetic field can be 1 trillion times stronger than Earth's. A special class called magnetars have fields 1,000 times stronger still. To give a whimsical, if utterly impractical, sense of scale, if a magnetar were located halfway between the Earth and the Moon, its magnetic field would be strong enough to erase the data from every credit card on our planet. It could distort the very atoms in your body from thousands of kilometers away. This fierce magnetism, combined with its density and spin, makes the neutron star one of the universe's most extreme and fascinating laboratories. Let's pause for a moment on that image. A smooth, spinning sphere of ultimate density, wrapped in an invisible cloak of devastating magnetism. It feels almost like a complete picture. But the universe, especially in its quietest corners, always has deeper layers, stranger truths nested within what we think we understand. So before we dive into the next cluster of facts about these stellar remnants, let's take a breath and look at the map for this entire gentle journey. We have 100 facts to explore, and to keep from getting lost in the cosmic vastness, we've gathered them into 5 distinct constellations of thought. The first group, which we've just begun to trace, is all about the bizarre nature of neutron stars. This is where we live in the sheer, unsettling weirdness of them, their composition, their behavior. The rules of physics stretch to a breaking point we can only dream of from our quiet corner of space. 20 facts that feel less like astronomy and more like quantum fairy tales. From there, we'll shift our gaze to a more fundamental, yet utterly intangible force. Our second constellation is pressure, the universe's invisible sculptor. This isn't about weather systems or deep sea diving. This is the pressure that forged the first atoms, that keeps stars from collapsing, that fights gravity in 1 billion silent battles across the cosmos. It's the story of why things hold their shape, from a gas cloud to a galaxy. Having armed ourselves with an understanding of the object and the force, we'll then turn to the record books. Our third group is cosmic record breakers. Here we'll meet the fastest spinners, the strongest magnets, the densest materials, and the most violent mergers. These are the superlatives of the universe, the gold medal performances written in gravity and light. But the cosmos communicates in more than just light. Our fourth constellation listens closely. Sounds and signals from the abyss. we'll translate the steady pulses of lighthouse stars, feel the ripples of colliding giants in space-time itself, and tune into the mysterious, fleeting radio whispers that hint at phenomena we're only beginning to grasp. This is the universe's soundtrack, played at a frequency meant for giants. Finally, we'll drift into more reflective waters with our fifth and final group, philosophies and futures. These facts are less about raw data and more about meaning. What do these extreme objects tell us about our place in the cosmos? How do they challenge our understanding of reality itself? And what practical or fantastical futures might they hold? This is where science gently bleeds into poetry, and where our exploration finds its quiet closure. 5 groups of 20, a century of cosmic curiosities, each one a stepping stone deeper into a restful, awe-inspired state. Think of it not as a textbook chapter, but as a slowly unfolding map of a dreamscape, where the laws of physics paint pictures stranger than any fantasy. We've already placed the first 5 points on that map. Now, let's continue tracing the contours of the first constellation, venturing into the heart of the neutron star itself, where matter exists in forms that have no name on Earth. Venturing into the heart of a neutron star is a journey into a realm of speculation wrapped in formidable mathematics. We cannot see inside, but the laws of physics, pushed to their limits, paint a picture of a bizarre inner world. This brings us to fact 6, the concept of nuclear pasta. As we move from the rigid crust down into the immense pressures of the inner layers, atomic nuclei can no longer maintain their familiar, separate spherical shapes. They are squeezed together so violently that they deform into long, cylindrical tubes, like strands of spaghetti. Deeper still, these tubes might flatten into sheets like lasagna. Even deeper, they may form more complex, bubble-like structures. Physicists playfully call this entire zoo of exotic matter forms nuclear pasta. It is thought to be the strongest material in the universe, with a tensile strength billions of times that of steel. A tiny fragment of this pasta, if it could be brought to Earth, would be utterly indestructible by any means we possess. But this dense, structured interior is not always serene. Fact 7 introduces the stellar equivalent of an earthquake, a starquake. The crust of a neutron star, while immensely strong, is under unimaginable strain from the magnetic fields locked within and the slowing of its spin over eons. Occasionally, this crust fractures and adjusts, it cracks. This sudden movement, a shift of perhaps just a centimeter across a landscape only kilometers wide, releases a colossal amount of energy. It's a tremor in the fabric of the star itself. These starquakes can cause sudden, tiny changes in the star's rotation rate, known as a glitch, and can unleash powerful bursts of X-rays and gamma rays. Imagine the deepest bass note of a tectonic plate shifting, but played on an instrument the size of a city and made of nuclear material. If we could somehow take the temperature of this object, we'd encounter fact 8, a staggering thermal paradox. The interior of a newborn neutron star is unthinkably hot, with temperatures in the core reaching hundreds of billions of degrees Celsius, hotter than the center of a supernova, hotter than anything in the present-day universe except perhaps the immediate aftermath of the Big Bang. Yet, the surface, while still insanely hot by human standards at around 1 million degrees Celsius, is relatively cool. This immense gradient is because the neutron star is an incredible insulator. Its incredibly dense interior is so efficient at trapping heat that it can take tens of thousands of years for significant cooling to occur. It's like a cosmic thermos, holding onto the fiery memory of its violent birth for millennia. This brings us to the topography of this smooth sphere and fact 9, the mountains. We mentioned earlier that the surface is almost perfectly smooth. Almost is the key word. Due to the intense magnetic fields and the sheer strength of the nuclear pasta crust, tiny deformities can persist. These are the mountains of a neutron star. But forget Everest. The maximum height a mountain can reach on a neutron star before its own weight crumbles, it is estimated to be less than a few centimeters, perhaps only a few millimeters. These microscopic mountains on an object with Earth's mass would be under such stress that a cubic centimeter of the mountain material would weigh as much as every human on Earth combined. They are not made of rock, but of incredibly dense, iron-like nuclei in a crystalline lattice, standing as minute, impossibly heavy wrinkles on an otherwise flawless sphere. All these properties, the density, the spin, the magnetic field, culminate in one of the neutron star's most famous and useful guises, which is fact 10. They are the universe's most precise natural clocks. When a neutron star's powerful magnetic field channels radiation into beams that sweep around like a lighthouse, and that beam happens to point toward Earth once per rotation, we call it a pulsar. The regularity of these pulses is astonishing. The first pulsars discovered were so precise that astronomers briefly entertained the fanciful idea they might be signals from an extraterrestrial civilization. Some pulsars, particularly millisecond pulsars, are stable to a level comparable to atomic clocks over decades. Their rhythmic ticking, a heartbeat born from stellar catastrophe, provides a celestial metronome against which we can measure gravitational waves, navigate spacecraft in theory, and test the very fabric of spacetime with exquisite accuracy. From a chaotic death arises perfect, predictable rhythm. Having explored the neutron star as a distinct, bizarre object, it's time to pull our focus back. To understand why it exists in this particular, extreme form, we must introduce its constant companion and creator, pressure. Not the gentle pressure of a hand, nor even the crushing weight of an ocean trench, but cosmic pressure, the fundamental, often invisible force that scripts the life cycle of everything. Our next group of facts shifts to this grander, more abstract sculptor. Fact 11 reframes our understanding. In everyday life, we think of pressure as a force that pushes outward, that compresses. In the cosmos, pressure is often a hero, a resisting force. Its primary cosmic role is to prevent the universe from immediately collapsing in on itself under its own gravity. It is the outward push that balances the inward pull. In a star like our Sun, it's the thermal pressure from nuclear fusion holding gravity at bay. In a white dwarf, it's the quantum mechanical pressure of electrons refusing to be squeezed together. In a neutron star, it's the neutron degeneracy pressure, the same quantum principle, but for neutrons making a last, desperate stand. Without these pressures, gravity would simply win, and all matter would endlessly condense. This leads to a subtle but beautiful point, fact 12, happening right now in our own solar system. Inside the Sun's core, the conditions for a runaway nuclear explosion are perpetually present. There is an immense amount of fusible hydrogen under tremendous heat and pressure. Yet, the Sun doesn't detonate like a bomb. Why? Because the very pressure created by the ongoing fusion reactions provides a stabilizing counterforce. The core is in a state of hydrostatic equilibrium. The outward pressure of the hot plasma perfectly balances the inward crush of gravity. This self-regulating balance is what allows stars to burn steadily for billions of years. The pressure isn't just a byproduct. It's the essential governor on the stellar engine. When a star exhausts its nuclear fuel and gravity begins its final victory, quantum mechanics steps in with a new kind of pressure. Fact 13 is about this quantum hero, degeneracy pressure. This isn't a force in the traditional sense of particles pushing against each other. It's a consequence of the Pauli exclusion principle, which states that no two identical fermions, like electrons or neutrons, can occupy the same quantum state. As gravity tries to squeeze electrons into the same space, they resist. They must occupy higher energy states, which creates an effective outward pressure. This electron degeneracy pressure is what supports a white dwarf. Crush it further, and electrons are forced to merge with protons to form neutrons. Now it's the neutron's turn. Neutron degeneracy pressure is what halts the collapse to form a neutron star. It is quite literally the last line of defense before the final surrender to a black hole. This pressure has no source in heat or motion. It is a fundamental, immovable assertion from the quantum world that says, no further. But pressure's influence isn't confined to stars. Fact 14 introduces the most mysterious and dominant pressure in the modern cosmos. The pressure of empty space, driven by what we call dark energy. We often think of space as nothing, a passive stage. But according to our best measurements, empty space itself possesses a kind of intrinsic repulsive pressure. This negative pressure or tension is what is causing the expansion of the universe to accelerate. It's a subtle, pervasive push that works against gravity on the largest scales. While gravity tries to pull galaxies together, this vacuum pressure is gently driving them apart, faster and faster. It is the quiet, dominant pressure shaping the ultimate fate of the entire cosmos. All of this culminates in Fact 15, the universal balancing act. The entire life, death, and afterlife of a star is a story of this duel between pressure and gravity. Gravity is the great unifier, the force that gathers dust into stars. Pressure is the great resistor born from nuclear fire or quantum law. A star lives as long as its pressure from fusion can balance its gravity. It dies when that pressure fails. What it becomes in death, a white dwarf, a neutron star, or a black hole, is determined by which new form of pressure, if any, can rise to meet the final gravitational challenge. It is a cosmic seesaw that has been tilting back and forth since the first stars ignited. Every glowing point in the night sky is a testament to this momentary and often billion-year-long truce. To appreciate the sheer scale of cosmic pressure, it helps to anchor it with examples a little closer to home before we let our minds drift back to the interstellar extremes. Fact 16 takes us to our neighbor, Venus. The surface pressure on Venus is about 92 times that of Earth's at sea level. To put that in a tangible, if dramatic, way, it is equivalent to the pressure found nearly a kilometer beneath Earth's oceans. This isn't just a heavy atmosphere. It's a crushing, supercritical fluid of carbon dioxide. A standard military submarine, engineered to withstand the deep ocean, would be crumpled like a paper cup on the Venusian surface. The pressure there is so immense that it has fundamentally shaped the planet's geology, preventing the kind of tectonic plate movement we see on Earth and contributing to a runaway greenhouse effect that bakes the surface at lead melting temperatures. It is a stark reminder that pressure is not an abstract concept, but a physical reality that defines worlds. From the crushing atmosphere of a planet, we travel to the ultimate limit of pressure itself, which brings us to fact 17. At the event horizon of a black hole, and especially at the singularity within our current understanding of physics breaks down, the gravitational pull, and thus the pressure required to resist it, becomes effectively infinite. We have no mathematics, no theory that can reliably describe the state of matter and space-time under such conditions. It is a realm where the concepts of pressure and density, as we define them, cease to have meaning. This isn't just a larger number on the same scale. It's the edge of the scale itself. It represents the point where the neutron star's valiant degeneracy pressure finally and utterly fails. That failure is not a quiet one. It is often preceded by one of the universe's most spectacular pressure-related events, described in Fact 18, the supernova shockwave. When a massive star's core collapses, the inrushing outer layers hit the newly formed, impossibly hard neutron star core and bounce. This creates a stupendous rebounding shockwave of pressure that races back out through the star. This shockwave is the primary engine of the supernova explosion. It does more than just tear the star apart. The energies and pressures involved in this blast are so prodigious that they forge elements heavier than iron, like gold, silver, and uranium, through rapid neutron capture, a process called the R process. This shock wave then hurls these newly minted elements, this stellar ash, out into the surrounding galactic space. The pressure from a dying star, therefore, is the cosmic pressure cooker that seeds future generations of stars, planets, and life with the necessary heavy elements. The iron in your blood, the calcium in your bones, were all forged in such cataclysms. The echoes of the greatest pressure event of all still resonate faintly around us. Fact 19 is about that echo, the cosmic microwave background radiation. This omnipresent cold glow is the afterimage of the hot, dense, pressurized state of the entire universe about 380,000 years after the Big Bang. At that time, the universe was a searing plasma of particles and light under immense pressure and temperature. As it expanded and cooled, the pressure dropped enough for atoms to form, releasing the light that has been traveling ever since. This radiation is often described as a snapshot, but it's more like a fossilized sound wave, the imprint of pressure oscillations that rippled through the primordial soup, whose faint patterns eventually grew into the vast cosmic web of galaxies we see today. It is the universe's oldest fossil, and it is a fossil of pressure. Finally, Fact 20 offers a reflective contrast. Human beings are remarkably adaptable to pressure in our own environment. We can train our bodies to dive deep into the ocean, enduring pressures that would crush an untrained person. We build vessels to explore the Mariana Trench, where the pressure is over 1,000 times atmospheric pressure. Yet, in the context of the cosmos, this is a trivial feat. The pressures that govern stellar interiors, neutron star crusts, and the vacuum of space itself operate on a scale so far beyond our biological and technological experience that they might as well be magic. Our everyday struggle with pressure is a psychological or physiological metaphor. Out there, pressure is a fundamental physical architect, indifferent and absolute. It is a humbling thought. The forces we navigate in our lives are gentle breezes compared to the silent, crushing hurricanes that shape the stars. Now, with a sense of the awesome power of cosmic pressure, we return to the neutron star, not just as an object, but as a champion, a record holder in the universe's grand competition of extremes. This group of facts is about the gold medals, the universe's mosts and firsts, many of which are held by or involve these dense remnants. Fact 21 states it plainly: neutron stars contain the densest stable matter we know of in the universe. The matter in their cores is packed so tightly that it approaches the theoretical limit before complete gravitational collapse into a black hole. While the singularity inside a black hole might be denser, it is not a state of matter we can observe or describe with known physics. The neutron star represents the ultimate endpoint of condensed matter that still obeys, albeit in extreme form, the rules of particle physics. It is the pinnacle of density that nature allows while still maintaining a tangible structure. This density and conservation of angular momentum lead directly to fact 22, the title of fastest spinner. The current record holder for the fastest spinning neutron star we know is PSR J1748-2446 AD, located in the globular cluster Terzan 5. It rotates a staggering 716 times per second. To visualize this, an object with more mass than our Sun, spinning so fast that its surface at the equator is moving at about 24% the speed of light. It completes a rotation in just 1.4 milliseconds. This isn't just fast. It's a blur on a cosmic scale, a testament to the incredible spin-up that occurs during the core collapse of its progenitor star. If the title for fastest spin is astounding, the title for strongest magnetic field is mind-warping. Fact 23 introduces the magnetar, a neutron star subclass where magnetic fields reach almost ludicrous intensities. While a typical neutron star's field is 1 trillion times Earth's, a magnetar's can be 1,000 times stronger than that, 1 quadrillion times Earth's field. These fields are so powerful they can distort the shape of atoms themselves, creating an exotic form of matter where quantum electrodynamics is tested to its limit. The energy stored in a magnetar's magnetic field is so vast that a sudden rearrangement, a magnetic starquake, can power brief, colossal bursts of gamma rays and X-rays that, for a fraction of a second, outshine entire galaxies. They are the universe's ultimate electromagnetic monsters. These bursts connect to another record, described in fact 24. Some of the most energetic, short-duration explosions in the universe are gamma ray bursts, GRBs. The leading model for the shorter duration class of GRBs, those lasting less than 2 seconds, is the merger of two neutron stars, or a neutron star and a black hole. In the final moments of such a dance, the two ultra-dense objects spiral together and collide. This collision releases more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. It is a flash of light so intense it can be seen across billions of light years, a brief, violent signature of the ultimate pressure cooker, forging heavy elements and rippling space-time itself. To understand the thermal extremes involved in these events, we look back to the beginning. Fact 25 reminds us that while neutron stars are incredibly hot, they are not the hottest things to have ever existed. That record is held by the universe itself in the first moments after the Big Bang. Within the first microsecond, the temperature of the entire cosmos was in the trillions of degrees, hot enough that the fundamental forces we know today, electromagnetism, the strong and weak nuclear forces, were likely unified into a single superforce. The pressures were correspondingly immeasurable. A neutron star's core, for all its ferocious heat, is a chill autumn evening compared to the white-hot forge of the universe's birth. It is a relic of that early violence, but cooled and condensed into a stable, albeit extreme, form. The cosmos has a peculiar habit of creating opposites, of placing the hottest and coldest, the most violent and the most serene in intimate connection. Fact 26 illustrates this beautifully. The coldest known place in the natural universe is the Boomerang Nebula, a preplanetary nebula about 5,000 light-years away. Their gas expanding from a dying red giant star has cooled to just 1 degree above absolute zero, colder than even the background glow of the Big Bang. And what is causing this stellar death and subsequent deep freeze? The intricate physics of stellar evolution, driven by the same balancing act between pressure and gravity that, in more massive stars, leads to the formation of neutron stars. The progenitor star here wasn't heavy enough to create a neutron star, but its death throes, a delicate shedding of outer layers, have created this frigid wonder. The coldest place we know is a monument to a quiet stellar death, a counterpoint to the infernal birth of a neutron star. From cold to utility, Fact 27 presents a futuristic application of neutron stars. The incredible stability of pulsar rotation, especially in millisecond pulsars, makes them potential galactic lighthouses for navigation. The concept of pulsar-based navigation involves using the precise timing of pulses from multiple known pulsars to triangulate a position in space, much like GPS uses satellites. For a spacecraft traveling far beyond the solar system, where Earth-based signals are too weak, detecting these cosmic beacons could provide a way to determine its location in the galaxy. Each pulsar has a unique signature, its period and direction, creating a sort of celestial map written in rhythmic light. It's a beautiful idea, using the steady heartbeat of dead stars to guide future explorers. Could these stellar corpses also be cosmic jewels? Fact 28 delves into a speculative but theoretically sound possibility. Under the immense pressures within a white dwarf, a less dense cousin of the neutron star, carbon could crystallize into a lattice, forming a diamond-like structure. Some models suggest that certain white dwarfs may have crystallized carbon cores, making them, in effect, Earth-sized diamonds. While the pressure in a neutron star is far too great for atomic bonds and traditional crystal structures, the concept speaks to the alchemy of pressure. The universe, under sufficient squeeze, can turn common elements into things of mythic value. A neutron star is not a diamond, but it is something far more strange and precious. A giant nucleus, a jewel of pure nuclear matter. These dense objects do not exist in isolation. They are part of a dynamic and sometimes violent cosmos. Fact 29 addresses their potential fate in binary systems. A neutron star in a close orbit with another star, or even another compact object like a white dwarf or black hole, can have a dramatic life. It can siphon material from its companion, a process that can spin it up to millisecond speeds, and also cause violent X-ray bursts as the accreted material undergoes fusion on its surface. In a more sinister scenario, if its companion is another neutron star or a black hole, they will slowly spiral together due to energy loss from gravitational waves, culminating in a catastrophic merger. A neutron star can, in essence, be eaten or destroyed by a more powerful gravitational predator. This merger process is not just destruction. It is also spectacular creation. Fact 30 reveals one of the most profound connections between these exotic objects and our own existence. The violent collision of two neutron stars is considered a primary site for the R process, the rapid neutron capture process that creates about half of all elements heavier than iron. Simulations show that such an event can forge staggering amounts of gold, platinum, and other rare Earth elements. In fact, a single neutron star merger is thought to produce an amount of gold many times the mass of our entire planet. The gold in a wedding ring, the platinum in a catalytic converter, the uranium in some reactors, they are all, quite possibly, the ashes of a cosmic collision that happened billions of years ago in a galaxy far away between two city-sized orbs of degenerate matter. We are literally made from the debris of stellar catastrophes. The universe, for all its visual splendor, is not a silent movie. It has a soundtrack, one written in radio waves, gravitational ripples, and high-energy particles. Our next constellation of facts tunes our ears to these cosmic frequencies, many of which emanate from or are influenced by neutron stars and the immense pressures surrounding them. Fact 31 is the foundational beat, the pulse. A pulsar's defining characteristic is its lighthouse-like beam of radiation, which sweeps past our line of sight with metronomic regularity. This isn't a sound in the traditional sense, but when the radio waves are converted into audio signals, they manifest as a sharp, rhythmic click or beep. The first discovered pulsar, PSR B 1919+21, had a period of 1.337 seconds, a steady cosmic tick-tock that baffled its discoverers. This regularity is the heartbeat of a dead star, a precise timekeeper born from chaos, and it forms the baseline for much of neutron star astronomy. But we can now listen to deeper, more fundamental vibrations. Fact 32 celebrates our new sense, the detection of gravitational waves from neutron star mergers. In 2017, the LIGO and Virgo observatories felt the space-time ripples from two neutron stars spiraling together and colliding 130 million light-years away. This was not sound traveling through air, but a literal stretching and squeezing of space itself, converted into an audible chirp, a rising frequency that ended abruptly at the moment of merger. For the first time, we heard the final moments of a cosmic dance that had been theorized for decades. It was a direct perception of gravity in action, a pressure wave in the fabric of reality. This leads to a fascinating thought experiment. Fact 33. If you could somehow stand on a platform near a rapidly spinning neutron star, you wouldn't hear its rotation through sound waves in the traditional sense, as space is a vacuum. However, the immense gravity of the star warps spacetime around it. Its rotation drags this warped spacetime along, an effect called frame dragging. Some theories suggest that if you had sensitive enough equipment, you could detect this dragging as a very low-frequency hum or vibration in the very structure of spacetime around you. It would be the sound of the universe's fabric being gently stirred by a spinning mass. Some of the most enigmatic signals in modern astronomy are the fast radio bursts, FRBs, from Fact 34. These are intense, millisecond-long flashes of radio waves that come from distant galaxies. While their exact origins are still debated, one of the leading theories involves magnetars, neutron stars with those unimaginably strong magnetic fields. A starquake or magnetic reconnection event on a magnetar could, in theory, release a colossal amount of energy in a radio burst powerful enough to be seen across the cosmos. These FRBs are like sudden, cosmic shouts in the radio static, brief and powerful messages that might be tracing the turbulent magnetic lives of these extreme objects. All this combines into Fact 35. The universe is far from silent. It is a symphony of pressure waves. The steady tick of pulsars, the chirp of colliding neutron stars, the hypothetical hum of frame dragging, the crackle of solar wind, and the ancient whisper of the cosmic microwave background. These are not metaphors. They are physical vibrations, oscillations in plasmas, space-time, and magnetic fields. Before the first stars ignited, the universe was filled with a dense plasma that could propagate sound waves, pressure waves, that left their imprint on the distribution of galaxies. We live in a cosmos that rings and hums and beats with the consequences of pressure, from the smallest quantum fluctuations to the collisions of dead stars. The symphony of the cosmos is not just noise. It carries profound information. Fact 36 highlights how the precise timing of pulsar pulses has become one of our most powerful tools for testing Einstein's theory of general relativity. In binary systems containing a pulsar and another neutron star or white dwarf, the intense gravity and orbital motion create subtle deviations in the timing of the pulses. By tracking these deviations over years and decades, astronomers have verified predictions of general relativity with incredible precision, such as the loss of orbital energy due to gravitational wave emission, for which the 1993 Nobel Prize was awarded, and the dragging of spacetime by a rotating mass. These dead stars, behaving as perfect clocks in a gravitational dance, are our most stringent laboratories for the laws of gravity themselves. To listen even further back in time, we have fact 37. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, is often visualized as a static map of temperature variations. But these tiny fluctuations, on the order of 1 part in 100,000, are the fossilized imprints of sound waves that rippled through the primordial plasma. In the first 380,000 years, the universe was so dense that pressure waves could travel through it. Regions of slightly higher density would pull in matter through gravity, only to be pushed back out by the increased radiation pressure, creating oscillations. When the universe cooled enough for atoms to form and become transparent, these waves were frozen in place. By studying the statistical patterns of these frozen sound waves, cosmologists can deduce the composition, geometry, and history of the entire cosmos. It is the oldest melody, encoded in microwaves. Not all neutron star music is in the radio band. Fact 38 reminds us of the high-energy performers. While radio pulsars are the most famous, many neutron stars reveal themselves through X-rays and gamma rays. In binary systems where a neutron star is actively accreting material from a companion, the stolen gas spirals in at tremendous speeds, forming a hot accretion disk. As this material finally crashes onto the neutron star's surface or magnetic poles, it is heated to millions of degrees, glowing fiercely in X-rays. Magnetars, with their monstrous magnetic fields, can produce spectacular gamma-ray flares. These high-energy emissions are a different movement in the symphony, a violent, percussive section compared to the steady radio rhythm. The most tragic and beautiful duet in this symphony is described in fact 39, the inspiral of a binary neutron star system. Two neutron stars, locked in a mutual orbit, lose energy by emitting gravitational waves. This causes their orbits to gradually decay over hundreds of millions of years. As they spiral closer, the gravitational wave signal increases in frequency and amplitude, the rising chirp detected by LIGO. In the final seconds, they orbit each other thousands of times per second before merging in a cataclysmic event that can produce a short gamma-ray burst and a kilonova, an explosion that forges heavy elements. This slow, inevitable dance toward destruction is a direct consequence of energy loss through ripples in spacetime, a duet that ends in a brilliant, transformative crescendo. All this cosmic noise, from the faint microwave hum to the violent bursts, forms a coherent narrative. Fact 40 ties it together. The noise of the universe is not random static. It is layered information. The CMB tells the story of the universe's infancy. The distribution of galaxies tells of the growth of structure from those early seeds. The chirps from neutron star mergers tell of stellar life cycles and the origin of elements. The steady pulses tell of the physics of extreme matter and gravity. By learning to decode these different frequencies, electromagnetic, gravitational, and perhaps one day neutrino, we are listening to the autobiography of the cosmos, written in the language of pressure, gravity, and light. It is a story still being told, and we are only just beginning to understand its grammar. Having journeyed through the what, the how, and the sounds, we now drift into the realm of the so what. What does it all mean? This final constellation of facts is less about data points and more about perspective, philosophy, and the quiet awe that comes from contemplating such extremes. Fact 41 is perhaps the most humbling. Neutron stars demonstrate that the universe is capable of creating realities stranger than any human imagination or science fiction. No writer conjured the concept of nuclear pasta or a magnetic field so strong it distorts the vacuum of space before science deduced their necessity from mathematics and observation. These objects exist at the edge of known physics, in a zone where matter is so compressed it ceases to behave in any familiar way. They are a testament to the fact that nature's creativity, driven by simple, unforgiving laws, far outstrips our own. The universe is not just weirder than we suppose. It is weirder than we can suppose. This makes them, as Fact 42 states, unparalleled natural laboratories. We cannot recreate the crushing pressures and densities of a neutron star core in any terrestrial experiment. The Large Hadron Collider smashes particles together at incredible energies, but it cannot create and sustain a cubic centimeter of degenerate neutron matter. Therefore, by observing neutron stars, their cooling, their glitches, their oscillations, we are conducting remote experiments on matter in its most extreme state. They allow us to probe the equation of state of ultradense matter, testing theories of nuclear physics and quantum chromodynamics under conditions we will never replicate on Earth. They are cosmic gifts to physicists. There is a profound beauty in this expressed in Fact 43. The existence of a neutron star is proof that the death of a star is not merely an end. It can be a transformation into something new, powerful, and beautiful. A supernova is one of the most violent events in the universe. Yet from that violence can emerge an object of exquisite precision, a pulsar, and the seeds for future planets and life. The gold in a jewelry store is the direct result of stellar death. The neutron star itself is a monument to that death, a diamond forged in the crucible of collapse. It redefines destruction as a creative, albeit brutal, act. This dance between creation and destruction is governed by forces that render our human concerns almost quaint. Fact 44 reflects on cosmic pressure as that great humbler. The pressures that shape stars and galaxies operate on scales and timeframes that dwarf human history. They remind us that the physical laws governing the universe are indifferent, absolute, and magnificently powerful. Our daily struggles, our triumphs and failures, play out on a stage that is unimaginably small and brief in the cosmic theater. Contemplating a neutron star can induce a kind of peaceful insignificance, a reminder that we are transient guests in a vast, ancient, and mechanically glorious cosmos. Yet, from this insignificance can spring inspiration. Fact 45 looks to a distant, speculative future. Understanding neutron star matter could one day inform new materials or energy sources, though such ideas are the realm of far future science fiction. More tangibly, pulsar timing arrays are being used to search for low-frequency gravitational waves from supermassive black hole mergers. The study of magnetar flares helps us understand plasma physics in extreme magnetic fields. The technology developed to detect their subtle signals pushes the boundaries of our engineering. The pursuit of understanding these distant objects invariably advances our capabilities here at home, lighting a path of curiosity-driven progress. The philosophical and practical threads we've begun to pull continue to weave a broader tapestry, connecting these distant, dense objects to the very stuff of our being and our potential future among the stars. Fact 46 makes this connection visceral and literal. For centuries, alchemists dreamed of transmuting base metals into gold. The universe performs this alchemy routinely, but not in a gentle process. The gold, platinum, and other precious elements in the Earth's crust were likely forged in the cataclysmic mergers of neutron stars, events that occurred long before our solar system formed. These elements, blasted into space by kilonova explosions, mixed with interstellar gas and dust, which later coalesced into the nebula that gave birth to our sun and planets. Therefore, every piece of gold jewelry, every microchip with gold connectors, contains atoms that were once part of a neutron star's fiery demise. We are literally walking around with fragments of stellar catastrophes. This leads to a fascinating speculative idea in Fact 47. Neutron stars, specifically pulsars, could serve as natural navigation beacons for any spacefaring civilization, including a potential future for humanity or hypothetical extraterrestrials. Because pulsars have unique, identifiable periods and are visible across galactic distances, a map of the brightest millisecond pulsars could function as a galactic positioning system. In fact, the plaques on the Pioneer spacecraft and the diagrams on the Voyager Golden records included a map showing the location of our Sun relative to 14 pulsars, using their periods as identifiers. It was a message in a bottle, telling anyone who might find it when and where we were, based on the steady ticking of these cosmic clocks. They are the universe's natural lighthouses. But for all we think we know, the heart of a neutron star remains one of physics' great frontiers. Fact 48 acknowledges a profound uncertainty. We do not know the true state of matter in the deepest core. As pressure increases toward the center, neutrons may themselves break down into their constituent quarks, creating a soup of free quarks and gluons, a quark-gluon plasma, or perhaps an exotic state like color superconductivity. It's also possible that strange matter, containing strange quarks, could be more stable than ordinary nuclear matter at these densities. The equation of state, the relationship between pressure and density, for such matter is unknown. Different theoretical models predict different maximum masses and sizes for neutron stars. Each new observation of a massive neutron star or a merger constrains these models, but the central mystery persists. The core is a realm where our standard model of particle physics may be incomplete. This cycle of creation under pressure is universal. Fact 49 widens the lens. The universe is a continuous cycle of building up and breaking down under the influence of pressure and gravity. Gravity gathers diffuse gas into stars. Nuclear pressure ignites them, forging lighter elements into heavier ones. When that pressure fails, gravity collapses the star, often triggering an explosion that scatters those new elements. The shock waves from these explosions can trigger the birth of new stars. Neutron stars and black holes are the end products of the most massive stars, gravitational anchors that continue to influence their surroundings. We and everything we see are the products of this endless pressurized cycle, ashes from one stellar generation becoming the building blocks of the next. Finally, Fact 50 brings it home, echoing the famous words of Carl Sagan. Every atom in your body, except for the primordial hydrogen, was forged in the heart of a star. The iron in your hemoglobin, the oxygen you breathe, the carbon that forms the backbone of your DNA, all were created through nuclear fusion in stellar cores or in the explosive deaths of stars. The calcium in your bones was likely forged in a supernova. The iodine necessary for your thyroid function was likely created in an event like a neutron star merger. You are not just living in the universe. You are a temporary, conscious collection of the universe's own processed materials. To contemplate a neutron star is, in a very real sense, to contemplate a distant, extreme cousin in the great family of matter that also constitutes you. Having traced 100 threads of fact and philosophy, let's pause to gather a handful of them to see how they intertwine into a stronger chord of understanding. This isn't a summary, but a moment of connection, highlighting 10 facts that, when placed side by side, reveal the elegant and brutal logic of the cosmos. First, the origin. A neutron star is the corpse of a giant star, collapsed under its own gravity. Fact 1. This collapse is halted not by heat, but by a quantum rule, the Pauli exclusion principle, which creates neutron degeneracy pressure. Fact 13. This pressure makes a last stand, creating the densest stable matter we know. Fact 21. But this matter isn't uniform. In the crust, it's squeezed into shapes like spaghetti and lasagna, the unimaginably strong nuclear pasta. Fact 6. This dense object spins, often hundreds of times per second, becoming a precise cosmic clock, a pulsar. Fact 10. Its magnetic field can be amplified to monstrous levels, creating a magnetar whose flares can outshine galaxies. Fact 23. When two such stars orbit each other, they lose energy, spiraling together in a dance that ends in a merger. Fact 39. The collision produces a flash of gamma rays, one of the universe's most powerful explosions. Fact 24. And forges heavy elements like gold and platinum, scattering them into space. Fact 30. This scattered stardust, including the iron from earlier supernovae, eventually coalesces into new stars and planets. The cycle is universal. Pressure and gravity in an endless duel, building up and breaking down. Fact 49. And from that debris on at least one world, life emerged. Thus, the atoms in our bodies, the iron, carbon, oxygen, were forged in these stellar furnaces and cataclysms. Fact 50. So, the connection is clear, from the quantum pressure that holds up a city-sized star, to the gravitational waves of its collision, to the elements that make up our very selves. We are linked to these extreme objects by a continuous chain of cause and effect. They are not distant curiosities. They are our ancestors and our alchemists. Why are these sleepy facts important? Because they replace the noise of our daily lives with a deeper, slower rhythm. They connect the frantic pace of our human world to the stately billion-year cycles of the cosmos. In that connection, there is a profound calm, a perspective that soothes the mind and invites rest. Understanding that we are stardust contemplating stardust is perhaps the most peaceful thought of all. Sometimes the most extreme concepts are best approached through gentle, even whimsical questions. Let's lighten the tone for a moment with a thought experiment that often springs to mind when contemplating these ultradense objects. The question for Fact 51 is a classic. What would happen if you fell onto a neutron star? The answer is a process with a delightfully serious name: spaghettification. You wouldn't simply crash onto the surface. The gravitational pull on your feet would be exponentially stronger than on your head, even over the height of your body, because you'd be so close to such a concentrated mass. This difference in force, the tidal force, would stretch you lengthwise into a long, thin strand of atoms, like a piece of spaghetti. This would happen well before you made contact. As you approached, you'd also be sideswiped by lethal levels of X-rays and gamma radiation from the hot surface and magnetic field. So, long before you could even perceive a surface, you'd be transformed into a stream of elongated, irradiated particles. It's a reminder that the environment around a neutron star is as hostile as any in the universe, governed by forces that treat complex structures like the human body with instant, utter disregard. A more pragmatic, if equally fantastical, follow-up is Fact 52. Could we ever mine a neutron star for its dense material or the heavy elements it might contain? Theoretically, the answer is yes, the resources are there. A teaspoon of neutron star material, Fact 2, or the gold forged in a merger, Fact 30, represents astronomical value. Practically, however, the answer is a resounding no, and likely will be forever. The distances are measured in hundreds or thousands of light years. The environment is lethal, as we just discussed. The material itself, under such immense pressure and bound by degenerate matter physics, would likely behave in unpredictable and dangerous ways if removed from that environment. It might expand violently or decay. And finally, the energy required to extract and transport even a gram of it would be many orders of magnitude greater than any conceivable payoff. So, while it's a fun notion for science fiction, neutron stars will remain pristine, untouchable monuments, not mining colonies. Now, let's turn our gentle inquiry toward the force that shaped them. Fact 53 asks, does cosmic pressure affect our daily lives? The answer is a profound yes in the most fundamental ways. The atmospheric pressure we experience is what keeps water liquid and allows our lungs to function. More deeply, the thermal pressure in the sun's core, Fact 12, is what provides the sunlight that powers Earth's biosphere. The pressure of degenerate electrons in white dwarfs contributes to the light of certain stars. Even the large-scale structure of the universe, shaped by dark energy's negative pressure, Fact 14, dictates the ultimate fate of everything. We are immersed in and dependent upon a hierarchy of pressures that operate from our planet's surface to the edge of the observable cosmos. It is the silent, constant background of existence. This leads to a playful, metaphorical comparison in Fact 54. Someone might ask, is the pressure I feel at work or in life at all like cosmic pressure? In a humorous, metaphorical sense, perhaps, can feel like a crushing force, a demand to condense your time and energy. But the key difference is agency and scale. Cosmic pressure is a mindless, physical law. It simply is. The pressure in our lives is often a complex social, psychological, or biological phenomenon, full of nuance and choice. And crucially, while cosmic pressure can literally create diamonds and gold, Your workplace pressure is unlikely to have such a physically transformative effect, though it might feel that way. The comparison is a useful reminder to sometimes step back and laugh at the sheer scale of the universe. Our worries, while real to us, are not governed by the laws of degenerate matter. We can at least take comfort in that. As we near the end of our factual journey, it's time to acknowledge the shadows at the edge of our understanding. For all we have learned about neutron stars and cosmic pressure, profound mysteries remain. These are not failures of science, but its frontiers, the quiet, unanswered questions that keep astronomers and physicists gazing at data and scribbling equations late into the night. Fact 55 confronts the central unknown. What is the true state of matter at the very heart of a neutron star? We've mentioned the possibilities: a soup of free quarks, a crystal of hyperons, strange matter, or a superfluid of neutrons. But which one is it? This is known as the equation of state problem. Every new observation of a massive neutron star, like those clocking in at over 2 solar masses, rules out some of the softer, more exotic models. Every measurement of a neutron star's radius from X-ray observations adds another constraint. The recent detection of gravitational waves from mergers provides yet another way to probe this inner mystery, as the way the stars deform before colliding depends on the squishiness of their interiors. Yet, the definitive answer remains elusive. The core is a realm where our known physics is stretched to its breaking point, hinting at perhaps new physics beyond the standard model. This leads directly to fact 56. What happens when even neutron degeneracy pressure fails? The answer is the formation of a black hole. There is a theoretical upper limit to the mass a neutron star can support, known as the Tolman-Oppenheimer-Volkoff limit, estimated to be between 2 and 3 solar masses. If a neutron star accretes enough matter from a companion, or if it is born from the collapse of a sufficiently massive core, it will exceed this limit. At that moment, no known force in the universe can withstand the crush of gravity. The neutron star collapses further, its radius shrinking to 0, and an event horizon forms. It crosses the threshold from being the universe's densest object to becoming a tear in space-time itself. The precise moment of that transition, the point of no return for matter, is a physics puzzle of the highest order. An even deeper and more pervasive mystery is fact 57. What is dark energy? We've described it as a negative pressure inherent to the vacuum of space, causing the cosmic expansion to accelerate. But its fundamental nature is utterly unknown. Is it a cosmological constant, a fixed property of empty space as Einstein once proposed? Is it a dynamic energy field that has changed over time? Or does it indicate a need to modify Einstein's theory of gravity on the largest scales? This form of pressure is the dominant component of the universe today, governing its ultimate fate, and we have almost no idea what it is. It is the greatest unsolved problem in cosmology. Finally, fact 58 asks, is a neutron star always the final state? For an isolated neutron star, the end is a slow, cold fade. It will radiate away its residual heat over billions of years, becoming a cold, dark, crystalline sphere. A black dwarf made of neutron matter, though the universe is not yet old enough for any to exist. However, in a binary system, its fate can be more dramatic: merger or total accretion by a black hole. So, while a neutron star can be an incredibly long-lived final state, it is not necessarily a permanent one. Its destiny is intertwined with its environment, a reminder that even these mighty relics are subject to the broader dynamics of the galaxy. While the mysteries beckon, the study of these extreme objects is not purely abstract. It drives innovation and opens doors to futures that sound like science fiction, but are grounded in rigorous science. The practical and aspirational applications form a quiet testament to human curiosity. Fact 59 explores the concept of a galactic positioning system, GPS. We already use networks of satellites for navigation on Earth. For interstellar travel, an analogous system could use pulsars. Because millisecond pulsars have spin periods that are stable over human timescales, and each has a unique period and sky location, a spacecraft equipped with an X-ray or radio telescope could, in principle, measure the arrival times of pulses from several known pulsars. By comparing these times, it could triangulate its position anywhere in the galaxy with remarkable accuracy. This isn't just theory. Early experiments have been conducted, including a NASA project called NICER/Sextant on the International Space Station, which successfully demonstrated pulsar-based navigation in orbit. It's a beautiful synergy, using the death throes of massive stars to guide the first steps of a spacefaring civilization. The extreme conditions within neutron stars also push our understanding of material science, as noted in Fact 60. While we cannot bring neutron star material to Earth, studying its theorized properties, like the strength of nuclear pasta, challenges our concepts of material limits. This research into ultradense matter informs fields like nuclear physics and quantum chromodynamics. Furthermore, the technology developed to detect the faint signals from neutron stars, incredibly sensitive radio telescopes, cryogenic X-ray detectors, and laser interferometers for gravitational waves, pushes engineering to new heights. The quest to observe these distant objects often results in spin-off technologies with unforeseen terrestrial benefits. A more profound understanding stems from Fact 61. Neutron stars are key to solving the cosmic origin of the heavy elements. For decades, the source of about half the elements heavier than iron was a major puzzle. Supernovae could explain some, but not the abundance pattern of the very heaviest, like gold and uranium. The 2017 detection of gravitational waves and light from a neutron star merger, followed by the observation of a kilonova whose spectrum showed signatures of heavy element production, provided the smoking gun. By studying these mergers, we are literally tracing the origin of the rare elements that make up our technology, our jewelry, and even parts of our own bodies. It completes the periodic table's origin story. Finally, Fact 62 highlights how neutron stars have given us a new sense for observing the universe: gravitational wave astronomy. Before 2015, our view of the cosmos was entirely based on light, from radio waves to gamma rays. The detection of gravitational waves, first from black holes and then from neutron star mergers, opened an entirely new window. This sense allows us to hear the invisible, energetic motions of massive objects. It lets us probe the moment of merger itself, a region obscured by debris in electromagnetic observations. The future of this field involves building more sensitive detectors on Earth and perhaps in space, like the proposed LISA mission, creating a global and eventually galactic network of ears to listen to the symphony of space-time ripples. Neutron star mergers are among the most promising sources for this new astronomy, promising to reveal details about gravity, nuclear physics, and the expansion rate of the universe itself. We have traveled from the violent birth of a neutron star to the quiet mysteries at its core, from the abstract force of cosmic pressure to its tangible echoes in our world. As we begin to draw this exploration to a close, let's gather these threads not as a list, but as a cohesive narrative, a lullaby of logic written in the laws of physics. The story begins with a star's end. A giant exhausts its fuel, and gravity, the great unifier, wins its billion-year duel. Fact 15. The core collapses, but is halted by a quantum whisper, the Pauli exclusion principle, creating neutron degeneracy pressure. Fact 13. What remains is a city-sized sphere of matter so dense a teaspoon weighs 1 billion tons. Fact 2. Its surface smoothed to near perfection by unimaginable gravity. Fact 3. Within, matter may take forms like nuclear pasta, the strongest material conceivable. Fact 6. This newborn corpse spins, sometimes hundreds of times per second. Fact 4. And can be wrapped in a magnetic field of mythic strength. Fact 5. 23. From this chaos emerges perfect rhythm. The pulsar, a lighthouse in the dark, ticking with the precision of an atomic clock. Fact 10. We listen to its steady pulse. Fact 31. And now, to the deeper music of space-time, the chirp of two such stars spiraling to their doom. Fact 32, 39. Their collision is a flash that outshines galaxies. Fact 24. And a forge that creates gold, platinum, and the seeds of future worlds. Fact 30, 46. All of this is orchestrated by pressure. It is the force that keeps stars burning steadily. Fact 12. The quantum rule that holds up dead ones. Fact 13. The shockwave that scatters stardust. Fact 18. And the mysterious dark energy stretching the cosmos itself. Fact 14. We are connected to this grand cycle. The atoms that construct us were forged in such stellar fires and cataclysms. Fact 50. We are, in a literal sense, the universe becoming aware of itself, contemplating its own most extreme creations. So, what is the beauty here? It is not just in the spectacular explosions, but in the serene aftermath. It is in the transformation of violent death into an object of perfect regularity and a source of creation. It is in the understanding that the same indifferent, absolute laws that crush stars also, through 1 billion chance operations, led to a planet where beings could emerge to wonder about it all. The neutron star, in its silent, fierce isolation and cosmic pressure, in its invisible, shaping hand, represent the two sides of the cosmos, the intensely focused and the infinitely pervasive. Together, they weave a story of constant change, of endings that are beginnings, and of a reality far stranger and more wonderful than we could invent. This story offers a profound kind of peace. It places our fleeting human concerns within a framework of majestic scale and timeless process. There is rest to be found in that perspective, a gentle quieting of the mind as it contemplates its own stardust origins and its place in this slow, beautiful, and violent cosmic dance. As the final notes of our cosmic lullaby begin to fade, it's time to gently transition from observation to interaction, from listening to speaking, if only in a whisper. This space is for you, the listener, who has drifted with us through these 100 facts. Fact 63 is an invitation to reflection. Of all the strange truths we've encountered tonight, from stellar spaghettification to golden kilonovas, which one lingered in your mind? Did the image of a perfect cosmic clock, born from chaos bring you calm? Or perhaps the thought of wearing stardust forged in a collision light years away? Everyone's mind latches onto a different piece of the puzzle. So, if you're still awake and your thoughts are drifting, I invite you to share in the comments below. Tell me which fact resonated most with you, or simply let me know where in the world you're listening from. Painting a mental map of listeners from different time zones, all sharing this quiet moment of exploration, is one of my favorite parts of this journey. And if this particular path through the cosmos brought you some peace or curiosity, there are other trails to follow. For Fact 64, I'd like to offer a few gentle suggestions for further exploration, should you wish to continue this mood another evening. For a breathtaking visual and narrative journey, Carl Sagan's classic Cosmos series, or its modern successor presented by Neil deGrasse Tyson, are beautiful companions. For the specific poetry of stars and their deaths, the book The Lives of Stars by Ken Croswell is wonderfully accessible. And for a more focused, serene audio experience, there are entire channels and podcasts dedicated to science-based sleep stories and ambient space soundscapes. Let the search for Cosmic Documentaries for Sleep or Astronomy ASMR be your guide. Finally, Fact 65 is a look ahead, a soft promise. The universe is vast, and its quiet stories are endless. If you enjoyed drifting through the extreme physics of neutron stars, perhaps you'd like to join me next time as we wander somewhere different. We might delve into the silent, frozen oceans of distant moons, where pressures create exotic ices. Or we could explore the deep time slumber of seeds, waiting millennia to germinate. Or perhaps we'll simply lie back and map the constellations, not by their shapes, but by the myths and mathematics woven into each star. The choice, as always, will be guided by a desire for calm, wonder, and a gentle unraveling of the world's mysteries to help you unwind. If that sounds like a journey you'd like to continue, consider subscribing. But only if these quiet explorations genuinely add a moment of peace to your routine. We have reached the final, quiet shore of our exploration. All that remains is to acknowledge the hands and minds that built the vessel for this journey, the silent work that allows us to picture these distant wonders from the comfort of our own quiet rooms. Fact 66 is about gratitude for the tools of vision. The stunning visuals of nebulae, the artist's conceptions of neutron star cross-sections, and the data visualizations of gravitational waves that often accompany talks like these come from a collaborative effort. We owe thanks to space telescopes like Hubble, Chandra, and the James Webb Space Telescope for their eyes on the cosmos. We are indebted to the tireless work of scientific illustrators and animators at institutions like NASA, ESA, and academic visualization labs, who translate complex data into images that our minds can grasp and find beautiful. The ambient music and subtle soundscapes that may have underscored this narration are the work of talented composers who understand the mood of space. This has been a collective dream shared across disciplines. Fact 67 honors the pioneers of thought. Our understanding of neutron stars did not spring forth fully formed. It was built over decades by visionary scientists, people like Jocelyn Bell Burnell, who as a graduate student first identified the periodic radio signal of a pulsar, opening a new window on the universe. Theorists like Lev Landau, who speculated about neutron-rich stars before they were discovered, and Subramanian Chandrasekhar and Robert Oppenheimer, who calculated the fate of collapsing stars. Contemporary researchers analyzing LIGO's gravitational wave chirps or modeling nuclear pasta on supercomputers continue this legacy. We stand on the shoulders of giants who dared to imagine the extreme. Now, for a final moment of pure atmosphere, let's paint one last, slow-moving picture with Fact 68. Imagine the screen or the darkness behind your eyelids. A single, isolated neutron star, now cold and dark after eons, drifts silently through a sparse region of interstellar space. It is not pulsing, not flaring. It is just a dark sphere, a perfect silhouette against the faint, diffuse glow of the distant Milky Way. Around it, space is not perfectly black, but filled with the softest, most tenuous nebula. Cosmic dust so fine it seems like a memory of color, perhaps a hint of deep blue or violet. A single, brighter star from our own galaxy shines peacefully in the far distance, its light unwavering. The scene is one of profound, absolute stillness and chill. This is the eventual fate of many of these stellar relics, to become dark, quiet wanderers in the eternal night. There is no sound here, only the slow, cold expansion of time. And with that, we have reached our 100th fact. They have been, I hope, a gentle cascade of wonder, a stream of consciousness about the universe that slows your own. From the quantum to the cosmic, from the birth of a pulsar beat to the origin of the gold in a ring, we've wandered a landscape shaped by invisible, immense pressures and the bizarre objects they create. Now, let the images gently dissolve. Let the concepts of density and pressure, of spin and magnetic fury, soften and blur at the edges of your thought. There is no more information to absorb, no more facts to connect. The work of the mind is done. Feel the weight of your body settling into the surface beneath you, the gentle, constant pressure of gravity holding you, as it holds moons to planets and planets to stars. This same force, in a different dose, in a different place, creates the wonders we've spent this time contemplating. But here, now, it is simply a comfort, a tether to the quiet earth. Listen to the space around you, the faint hum of electronics, the distant sigh of a car, the rustle of fabric, or the absolute silence of the late hour. These are the small, close pressures of your environment, the gentle soundtrack of your own little corner of the cosmos. They are real, and they are here, and they are enough. The universe will continue its grand, silent work without your attention. Neutron stars will spin in the dark. Pressure waves from long-dead stars will still ripple through the interstellar medium. The cosmos expands, indifferent and beautiful, and that is perfectly all right. You have permission to release it, to let it all recede into a pleasant, distant hum. Bring your awareness back to the rhythm of your own breath. Inhale slowly, feeling the air fill your lungs. A tiny, personal exchange of pressure with the atmosphere. Exhale slowly, letting go. With each breath, imagine the vastness of space you've been holding in your mind softening, becoming diffuse, like a cloud of stardust dispersing into a peaceful, dark sky. There is no need to grasp any of it. The knowledge is not a task to be remembered, but an experience to have felt. Let it be like a dream you half remember upon waking. A sense of awe, a feeling of scale, a quiet wonder that lingers without sharp edges. Your thoughts can be slow now, like drifting clouds. Your body is heavy, supported, safe. The infinite complexities of degenerate matter and dark energy are not your burden to solve tonight. They are stories told to lull the restless mind into a state of awe-filled peace. You are a collection of atoms forged in stars, lying on a world shaped by gravity, listening to a voice woven from electrons and intention. For this moment, that is the only fact that matters. It is a fact of profound connection and profound simplicity. Rest in that. Let your eyelids grow heavy. Let the darkness behind them be as deep and peaceful as interstellar space. There is nothing more to do, nowhere else to be. Just this breath, and the next, and the quiet, endless wonder of existence, felt but not examined, known but not defined. The journey is complete. 100 whispers from the edge of reality have been shared, from the quantum standoff in a neutron star's heart to the silent push of dark energy in the void. We have traveled together through the life and death of stars, through forces that shape galaxies and forge the very elements of life. We have listened to the ticks of cosmic clocks and the chirps of colliding giants. We have found connections between the unimaginably distant and the intimately personal, resting in the knowledge that we are, all of us, stardust adrift in a beautifully mechanical, endlessly surprising universe. Thank you for allowing me to be your guide on this quiet exploration. Wherever you are, whatever hour it has become, I wish you a deep and peaceful rest, filled with dreams as vast and calm as the cosmos itself. Good night.